This is a short video about 4.3.1 Euler's proposition. This is the second step to Gauss's proof of the quadratic reciprocity theorem. So before we get into Euler's proposition, let's look at some notation here. If you take two rational numbers a and b, the interval from a to b intersects z. What should that denote? I just want that to be just what are the integers between a and b. So like for example, if I'm looking at 1/2 to 10/3 intersect z, you could think about drawing that on a number line. Here's 0.5, 10/3 is like 3.3 repeating. I'm just asking you to figure out what are the integers between there. So it would be 1, 2, and 3. So this would be the set 1, 2, 3. So don't let this notation scare you. Now, what we're about to do is a pretty important lemma that we're going to need for Euler's proposition. And what is this lemma here? Take two rational numbers a and b. Then for any integer n, what's going on? Remember, this notation is the same thing as asking for what's the cardinality of the following set. If you're coming from the proofs class, you probably didn't use this. You probably just used the bars. We're doing the same thing. So our book just likes to use this hashtag looking thing. So what are we saying here? Notice that we're taking some congruence mod 2. Remember how to think about mod 2. Mod 2 is determining if something's even or odd. You know, something's even if it's congruent to 0 mod 2. That means it's divisible by 2, right? And something's odd if it's congruent to 1 mod 2. So what are we saying? We are saying that the number of things in this set, if it's even, then the number of things in this set is even also. And the other thing it says is if the number of things in the set on the left is odd, well, then the number of things in the set on the right is odd as well. So these two sets, their cardinalities are of the same parity. They're either both even or they're both odd. And maybe that makes sense, in some sense anyway, because like what's the difference here? Well, I just added 2n to the right endpoint. And what we're going to see is that that is just going to add 2n integers to each of these sets. So, you know, when I add an even to something that's already even, it stays even. Or when I add an even to something that's odd, it stays odd. That's really what this is saying. And it's the same behavior if I take 2n away from the left endpoint. Again, the parity of the cardinality of each of these sets is the same. If the left is even, then the right is even, and vice versa. If the left is odd, then the right is odd as well. So again, I'm not saying that each of these sets have the same number of elements. I'm just saying that both numbers are either even or odd. And all this is contingent upon the fact that you need to make sure you choose a and b far enough apart so that there are actually some integers between them. Otherwise, this lemma is not true. Okay, so what's the proof of this look like? Before we get into Euler's proposition, we need to do this. So this notation here, that's the symbol for the ceiling of x. So x is any real number. The ceiling of x denotes the largest interval that's greater than or equal to x. So like the ceiling of 2.9 would be 3. What are we going to do now? I'm going to think about this interval from a to b plus 2n, and like that's topical because like, oh, that's one of these I'm supposed to consider. And what we're also going to start with is let's start with n as a positive integer here. And then we'll do another case when n's a negative integer. But for right now, let's let n be positive. Then what I'm going to do is I'm going to take this interval from a to b plus 2n. So here's a, here's b also, and then here's b plus a little bit more, b plus 2n. And I'm going to think about that interval all the way across. I'm going to think about it as this from a to b, that open interval, union with closed on the left and open on the right. If I take the union of the orange and the green, I get the whole interval from a to b plus 2n. All right, so what are we doing there? What we're going to do is figure out, well, how many integers are in just this green interval from b to b plus 2n? And if I count those then, if I count how many things are in there, well, one thing that would be in there, oops, I didn't want to delete those. Let's get those back in there. So if I count just what are the integers from here to here, well, the ceiling of b should be in there. So should the ceiling of b plus 1 up to the ceiling of b plus 2n, but maybe minus 1, right? Maybe the ceiling of b plus 2n actually would probably take me a little bit past that right endpoint. But if I subtract 1, then I'm guaranteed to be just to the left of that right endpoint, b plus 2n. Now what I want to do is I just want to count. How many integers is this? This is a list, and I mean it says right here it's 2n. But think about it. You have plus 0, plus 1. We're trying to do the counting here, and I stop when I get to 2n minus 1. If I started at 0 though, and I end at 2n minus 1, that's why I have 2n things in this list. So what are we saying? When I add in this extra little green interval, I'm just adding an even number of integers. And like we said before, if I add an even to an even, it stays even. It doesn't change the parity. And if I add an odd to an odd, an even to an odd, it doesn't change the parity. It stays odd. So what we just justified is the first congruence here. We just justified this thing. Now what we're going to do, at least in the case that when n is positive, I need to be able to do this for any integer n. So let's look at the case here again when n is negative. What does that look like? So what if that is actually of the form b minus 2n? So now I'm down here. And I want to think about, well, what's a way to think about b minus 2n here? So this interval from a to b minus 2n, well, that number is a little bit to the left of b now. So now what I'm going to do is I'm going to think about, well, a to b is the big interval now, right? You see a to b is the big one, and I've got maybe these two pieces. But the way that I want to think about a to b minus 2n, which is right here, I want to think about it as the whole interval, just minus this thing from b minus 2n to b. And by the exact same logic as before, if I count the number of integers that are in the orange now, so if I count the number of integers that are in the orange, that again is going to be 2n. In particular, it's going to be even in that case. So either way, right, we're always just like, adding or taking away an even number of integers, whether it's plus 2n or minus 2n, depending on, what n is. So since we're always adding or taking away an even number there, again, the parity is not affected. So all together now, what we've shown is that this first congruence holds for every integer n. Doesn't matter if n's even or odd. Now, you could do a similar argument to show this bottom one here. What if you take 2n away from the left endpoint? Or, since n can be any integer, what if you secretly add 2n there, right, if n's negative? It should be the same kind of argument that shows that it's true. Now this lemma 4.33, I'm going to refer to it again soon. It's very important for Euler's proposition. And what is Euler's proposition? It's really, in some sense, the hardest part about the quadratic reciprocity law. And so what's it say? So again, due to Euler here. If I've got an odd prime, or I've got p that's an odd prime, and let's take a to just be a positive number where p doesn't divide a. If q is a prime, where q is equivalent to either plus or minus p modulo 4 times a, ooh, that's interesting, then the Legendre symbols of a mod p and a mod q are the same. This is a super duper long proof, so I think what might be more instructive is to try to go through the proof with some specific p's, a's, and you'll see later q's and r's. So we're not going to actually do the proof. I just want you to kind of see what's going on, because as you see, it's pretty involved and easy to get lost. But I hope that this video helps you at least track through what's going on and helps you see and maybe believe it a little bit better. So I used these numbers before in the previous video that I made, where what if I took p to be 7, and what if I took a to be 4? Then I want to construct this set S now, and I'm only supposed to take the first p minus 1 over 2 multiples of 4. And in my case, p minus 1 over 2, that would be 3. So in my case, my S is just going to be the integers 4, 2 times 4, which is 8, and the last one, 3 times 4, which is 12. So in my case, my S is just that, because that's where my p1 minus 1 over 2 is. So I'm going to hold on to that. And now what I'm going to do is I'm going to build this union of intervals I. And so in my case, I've got a p I'm telling you about. Let me show you what it would be. So I would look like the interval here. So I'm going to do, 7 halves to 7, union, a bunch of other stuff. And I see that I'm supposed to stop when I get to this b minus a half times p to bp. And what is this b that they speak of? I didn't tell you about a b. Where b is either 1/2 a or it's 1/2 a minus 1. Which one of those do you pick? You pick whichever one's an integer, right? They're not both integers, only one of them is. Well, in my case, a we're working with is 4, so this one would be the integer. So b in my case is just going to be 4 over 2, so 2. Okay, so if b is equal to 2, then how many of these do I actually need then? I think I'm going to have 2 of them in this case. So I'm just going to have, the next one would be, according to this thing, well, the next one is this 3/2 p to 2p. And what would that be? That would be 3/2 times 7. So what is that? 10.5. I'll write it that way. And then to 14. That sounds good. I'm like waiting for a response as if there's going to be one in that case. So that's this is what my I looks like, and I know to stop there because b was just 2, so there should only be up to 2 times p. So there's 2 times p. That's where I stop. So my I just has this union of these 2 intervals here. Now what else are we going to do? We are going to look at my elements of S. So every element of S that's equivalent mod p to something in the interval from minus p over 2 to 0, I need to make sure that that actually lies in this interval I. So maybe you remember from before, here is my S's, and what I want to know is which ones of these are in the interval from, in this case, minus 3/2 to 0. And so maybe it would be helpful if I thought about this set S. I'm going to just write it up here. If I want to be between minus 3/2 and 0, I'm going to think about -4 is really equivalent to -3 mod 7. 8 is equivalent to 1 mod 7, so that's not helpful. And so I'll just write it as 1, equivalent to 1. What does that say, though? You can't see that at all, can you? Equivalent to 1. And then 12 was equivalent to -2 mod 7. So the point then is that, okay, 4 and 12 were the things in S that would be in this interval from minus 3.5 to 0. All right, so then what have we got, though? Well, minus 3.5 and 0. Well, let's look at 4 and 12, rather. 4 and 12, 4 is in this one, and 12 is in this one. So the point, though, is that I, it contains all the things in S whose residue, mod 7, lies in this interval minus p over 2 to 0. Right, so I contains both of the highlighted points in S that I have. And that's good for us. And so why is this good? I see that it has exactly 2 points. So what if I took S intersect I? Well, S intersect I, we see, is just 4 and 12. And what I notice is that the number of things in S intersect I is equal to 2, right? The cardinality of that set's 2. And maybe from the previous video about Gauss's lemma, I remember that, well, look, the ones that are negative, that's your nu. That's the exponent on -1. And that gives this Legendre symbol. So where are we at so far? So I'll write it this way. The Legendre symbol of A over P, so 4 over 7, would be equal to -1 to the nu. That's the same thing, though, as -1 to the cardinality of S intersect I. And so what do I know? I know that that's nu from the previous video. This is equal to nu. And what do I want to show going forward here? I want to show that this exponent, that it only depends on 7 mod 4a. Well, a is 4 also, so that'd be 7 mod 16. So that exponent there only depends on 7 mod 16, which again is the same thing as p mod 4a. So that's what I'm going for now. That's my goal, to try to show you that in blue. Why does it only depend on 7 mod 16? Okay, and so let's see, where are we at here? We are here as far as the proof goes. So the Legendre symbol of A over P is -1 to how many things are in S intersect I. And we're just demonstrating that with an example. And now what we're going to try to do again, it says we're going to compute the number of things that are in S intersect I. I already know that it's 2, but I want to show you again in blue, why does that only depend on 7 mod 16? So that's where the rest of this is going to go. And I'm going to do that off to the side, and it's going to follow what's going on here as well. So if we do that, what are we going to make? Well, the first thing we're going to make is it starts talking about 1 over AS and 1 over AI, and those are sets. And I want to tell you what those are. Well, in my case, A is 4, so 1 over 4S, all I'm saying to do is take S and rescale it by 1/4. So like S was 4, 8, and 12, so 1/4 S should be 1, 2, and 3. So that's kind of easy. And what else? 1/4 I, same idea. Just rescale all the points you see, all the endpoints you see from I, just rescale those by 4. And how do I want to think about those? I want to think about those as well. It was 3.5 over 4, and 7 over 4 then, union. The next one you'd have is 10.5 over 4, and 14 over 4. And if you simplify those a little bit in case it's helpful, this would be 0.875 to 1.75, union 2.625, if you do that as a decimal, say, to 3.5. All right, so that's 1/4 I here. And now what I want to look at is, well, what's the intersection of these two? What is the intersection there? Like, let's actually compute it in my concrete example with some numbers. And so maybe it's helpful for me to instead look at the decimals. That helps me. And I see that, well, 1 is in this one, and 3 is in this one. And notice again that, hey, that's also, the same two things. Those are the same two things from S that corresponded to the things that are the negative numbers in the interval minus b over 2 to 0. So anyway, 1 and 3 are in there. So that, how many things are in there? There's still 2 of them in there. That's the same as how many were in just S intersect I. And what else am I doing here? If I just counted, well, how many integers are in this interval here? I just counted. It's 1 and 3. All right, so there's 2 of them in there as well. So the number of elements in each of these is the same. So that's what all these equalities are trying to say to me here. What I'm going to do is get a little bit fancy now. What's another way to think about this set 1/4 I? What's another way to write that? And it turns out another way to write that, in my case, I just need these first two here. I'm going to think about it as, in my case, 7 over 2 times 4, so 7/8 to 7/4. So let's write that off to the side. So I can think about 1/4 I. I'm going to rewrite it as, what did I just say? I just forgot. 7/8, because hey, that's the same thing as 8.75. So 7/8 to 7/4. And then the other one would be union 21/8 to 14/4. All right, so I'm going to rethink about I that way. And why are we going to do this now? Now what we're going to do is we're going to bring in this, where's this 4a coming from? Where's this stuff equivalent mod 4a coming from in here? So where am I trying to go? I'm going to bring this into the picture now. I can take my 7. 4a for me is 16. I'm going to write 7 as 16 times something plus an r. And I get to choose whatever I want. And so what do I want to do? I'm going to say that, okay, 7 is equal to 16a plus r. What's convenient for me? Let's say 7 is equal to 16, not an a there, sorry, c, 16c plus r. So I'm going to say 7 is equal to 16 times, let's say c is -1, so that means r would be, what, 23? So what I'm going to do now is I'm going to make a new set. So my r here is 23. So r is 23, we've got that down. And what I'm going to do now is I'm going to make this new set J that they reference right here, where I hope that you see, if you compare J here with 1 over A times I, it really looks like I'm just replacing all the P's with R's. So, I mean, check that out. You literally are just replacing all the P's with R's. Okay, let's do that. So here is my example. Let's replace everything that I see with an R, with my 23 instead. So J for us is going to look like, well, 23/8 and 23/4 union. Remember, what is this one? This was really 3 times P, and this was really 2 times P. So now I'm going to do 3 times R and 2 times R. So 3 times R I think would be, well, 23 times 3 is how much? 69/8. and 46/4. And what I want to do is now I want to, just like the book says, let's compare. What's the difference between the endpoints of 1 over a times I and j? So let's look at the difference between these two endpoints here. Well, the difference between 7/8 and 23/8 is an even number, right? What'd you do? You added 16. You added 16/8 rather, and that's an even number. So when I mess with the left endpoint, if I'm just adding an even number to the left endpoint, we just got done proving this result that says, well, if you just rescale the left endpoint by an even, that doesn't change the parity of how many things are in that set. Interesting. And there's nothing special about this endpoint, right? If I compare those two, it's off by an even. If I compare these two, it's also off by an even. If I compare these two, it's off by an even. And if I compare these two, it's off by an even. So the difference between 1/4 I and j, it's always going to be the case that you're just changing the endpoints by the addition of an even integer. And he works it out here in general for you, which is great. But now we can invoke our lemma 4.3.3, which says that, again, my exponent nu, that's really the exponent on -1 that's going to really determine the Legendre symbol sign. That should be how many things are in z intersect 1 over a times I. But what we just showed is that that's also the same that's the same parity, at least, mod 2, it's equivalent to the number of things that are in z intersect j. Cool. So why is that good for me? What does that do then? So what that does for me is it tells me that that exponent nu, it depended on a, and it also depended on the r that I had. And so in particular, because I wrote p as, where am I? Okay, as I wrote p as 4ac plus r, that's what tell me that the parity of the cardinality of that set, it only depends on what is p mod 4a, right? Because it only depends on that r and that a. So we are here. So whatever that exponent is, -1 to that power there, it only depends on r and on a. And so in particular, because we wrote p as, again, 4ac plus r, it means it really only depends on p mod 4a, right? That's what it means to depend on that r. So what have I got then? If q and p are two things that are equivalent mod 4a, then ta-da, we should have that same nu that works for both of them. Therefore, a mod p's Legendre symbol is the same as the Legendre symbol of a mod q. That's one case. That's cool. What's going on in the lemma, though? Well, I need to show what happens if q is equivalent to minus p mod 4a. That's cool. We did all the hard work already. Oh, I went past it, sorry. And so now where are we at? Now we are here. What if q is equivalent to minus p mod 4a? Then all we're going to do is we're going to replace the r's that we had above by 4a minus r. And the way that I'm going to do that, I'll do that off to the side with my example. So my r earlier was 23. So we're going to replace 23 by 4, so 4a is 16 still, so by 16 minus 23, which is -7. All right, so what do I have then? I've got -7. Okay, yeah, we already said that. So what we're going to do then is we're going to take our j, where j had all these r's here, and I'm saying to take all these r's and replace them by 4a minus r, 4a minus r, 4a minus r, etc. So what's that look like in my example? So here is my j, and it's right here. And so how I'm going to write this down, I'm going to write this, and they call it k now, right? And they simplified k a little bit more. I'm going to write it this way, though. So for us, k should be equal to, remember I just have the 2, it would be 4a minus r over 2a. 4a minus r over 2a. Oh no, that's not right. 4a minus r over just a, my bad. Over a. Union 3 times 4a minus r over 2a, and then 2 times 4a minus r over a. Alright, so again, for us, for our example here, this is our j. We just needed these first two since I picked some small numbers here, and I just replaced the r's with 4a minus r. And let's actually plug in right what that is. Oops, I should have got rid of that. There. So remember, that's just 4a minus r is just minus 7. So this should be now minus 7/8 to minus 7/4. Union, this would be minus 21/8 to minus 14/4. So that's where we're at with that. Now what I want to do is I want to compare that. I'm told to compare k to the set minus j. All right, what's minus j look like? Minus j throws a minus sign on each of these guys. So that's all that it does. So maybe I've got an idea because I'm smart sometimes. Compare this to minus j. So minus j just puts a minus on all of these here. And what I want to do is, again, compare this to this. What can you say about them? And again, you can say that these endpoints from here to here, those are off by an even number, right? Those are just off by, what, negative 16/8? That's an even number. That's, how many, negative 2? Similarly here, these two endpoints, they're only off by an even. These two endpoints are off by an even. And finally, you guessed it, these two endpoints are off by an even. So what does that buy me? Again, lemma 4.3.3 tells me that how many things are in z intersect k is at least the parity. If there's an even number of things in z intersect k, say, well, then there's also an even number of things in z intersect minus j, and thus in z intersect j. And so what does that tie back into? From before, I knew that this was the Legendre symbol of A mod P from what we did earlier. And what this represents now with this K, with this 4A minus R, and that was under the assumption that Q is equivalent to minus P mod 4A. And so this would be the Legendre symbol, I guess minus 1 to these powers. Sorry, I'm not being very precise with that. So these things are equivalent mod 2. Let me finish that. Got a little bit ahead of myself here. So minus 1 to the z over to the z intersect k, how many things are in there, would be equal to minus 1 to the number of things in z intersect j. And again, what I'm trying to say now is that that's exactly the Legendre symbol of A mod P on the right from what we just did, and on the left, this is the Legendre symbol of A mod Q. So once again, no matter what, if Q is equivalent to P modulo 4A or equivalent to minus P modulo 4A, then Euler's proposition says that those two numbers have the same Legendre symbol.